Now, as we look at Module 7 here, there is something just a little bit different because we have two subjects here. What I decided to do was I have practice problems pertaining to the friction subject, and that'll be worth 10 points like normal. And then another set of practice problems that are dedicated to just the centroid. So another 10 points there. So two sets of practice problems here. And then one set of application problems, which we'll have them all on. Okay, so just broke that out a little bit for the practice problems. If we look at the learning plan, okay, so for the friction, we are going back into our McGraw-Hill textbook. Okay, so we'll be referencing that this evening, and the practice problems or the handout that we have here is going to go along with the McGraw-Hill. You can see the sections that we're going to be going over for that. Now, as we look at the guided notes here, these are the ones that I have copies of here in class, but we're going to be doing the friction guided notes this evening, which again are going to pertain to that chapter 4 out of the McGraw-Hill ebook. As we look down the page, when we get into the centroid section, they don't have just centroids in this book. So I have a handout for that. So that's going to be a chapter 9 handout. And we're only going to do the first part of that chapter. It's only going to be the centroids part. So we're not going to do that full chapter 9. That's why I have the pages listed here. Just the first, looks like 12 pages or so. And then the guided notes for that are going to be down here. I don't have those copies here yet. I have them running on the copy machine up there. I didn't want to take more time to wait for those. So I'll bring those in when we go on our break, but you can also print those off yourself. And again, like I said before, this time we're going to have two sets of practice problems just because it's kind of like two separate sections or two separate subjects, but then common application problems as we will see. So what I'm going to do is I already have my guided notes underneath my camera here, and I also have the chapter pages from the book. So I am going to start by opening up my document camera so we can look underneath here, and we'll start looking at chapter 4 on friction. Okay, in a little bit. All right, so if you look at your McGraw-Hill textbook, so if you're referencing that ebook, you want to go to pages 202, and then we're going to extend to about 218 for the friction part. So we have looked at chapter 4. I think it was in our module 5 equilibrium. And this is like the last, part of that chapter. So I've got some guided notes here. You're welcome. I encourage you to read the chapter here or the sections that I have specified in that learning plan. And that'll give you a little deeper understanding, but I want to hit the highlights here through the guided notes that we have. So here it says blank is a force that occurs naturally when two surfaces move relative to one another. So as you can imagine, we're talking about friction. This is going to be friction is a force. Okay, friction is a force that occurs naturally when two surfaces move relative to one another. Okay, dry friction occurs when two surfaces in contact are unlubricated. Okay, when we talk about statics, we aren't going to have, most of the time, the elements that we're talking about or the bodies that we're talking about are not moving. So they just simply friction or lubrication isn't necessary. When you get things that are moving relative to one another, then you're usually interested in friction so that you can minimize wear, that you can kind of minimize heat, and that the surfaces run nicely to each other. But in statics, we are going to be only concerned with dry friction. Now, here you're going to notice that we have some elements here. I want to bring in figure 411, which is right here. I'll kind of zoom in. Okay, there we go. Now, this figure has 3 parts to it: part A, part B, and part C. And we're going to be talking about each one. As we look at part A to start off with, if we have a block that is not moving, okay, remember, friction only occurs, it's only present when we have surfaces that are moving relative to one another. Okay, so when it's not moving, we have a block that's just sitting there, and there's 2 forces acting on it. The 2 forces are going to be the weight itself So that's going to be the W that we see here pointed down towards the center of the earth. Many times that's given, or sometimes we have to calculate it. But then you're going to notice that the other force acting on our block is going to be the support or the normal force. That normal force is always going to be perpendicular to the surface that that body, in this case, the block, is riding on, okay? So always perpendicular. Now, over on the right-hand side, you'll notice that, or to be the illustration to the right, you'll notice that we have a force P, kind of like a pushing force that's going to now kind of push on that block. And you can imagine if we have a pushing force going to the right, that block would end up moving at some point to the right if we applied enough load to that, okay? So you'll then notice that when we get this moving, there is an opposing force F here, okay? That's a friction force. Notice that it's down where you have the interaction between the block and the surface that it's riding on, and it's called F, okay? So when we start moving, there is a force, and that friction force, as you can imagine, is always going to be going and pointing in the direction opposite to the motion that's impending, okay? Now, over on the right-hand side here, this is a nice little graph. I like this graph because it gives us a pictorial of how the friction forces act in relationship to the applied force, okay? So as we look here, let's look first at the axes. The horizontal axis is going to represent the force P, the pushing force, okay? The vertical axis is going to represent the friction force, okay? So you're going to notice here that for a while at the beginning here, there is a straight line, and it is at a 45-degree angle, okay? 45-degree angle. And that's significant because what that says is there is going to be a section here where the friction force is going to be equal to the pushing force. And this is when we have no motion. That means it's at rest. Now, in this book, I'm not crazy about this terminology, but they refer to this as equilibrium. Okay, that's this part right here. I like to say at rest. Okay, because equilibrium, we can have static equilibrium, which is what they're referring to here, but we can also have dynamic equilibrium. All right, as you know from physics. All right, you can be moving and be in equilibrium. That's when you have constant velocity, right? There's no acceleration. So to say equilibrium, I think, is a little misleading because, again, you can have two different conditions of equilibrium. So on the left-hand side here, this is at rest. So what that means is, for instance, this block is in contact with a surface. Let's say there's a little bit of maybe it's on a carpet, all right? And that block has some significant weight. And if I want to try to push that, there is going to be a series of forces that as I push, it's not going to move, right? I'm going to push on it, it's not going to move. I'm going to push on it, it's not going to move. And if that's the case, if I'm in static equilibrium, the force that I push on it with, right? I'm sorry, this way, the force that I push on it with is going to equal the friction force. And that just means I'm not moving, okay? So I'm going to increase my pushing force, all right? And if I'm not moving, it's going to equal that friction force. It's in equilibrium. It's not moving. But I'm going to get to a point right here. This is called FM. That's the maximum friction force. It's the highest force on that graph. And what that tells me is that's the force that I am going to apply for which I'm just about to start moving. It's like motion is going to happen any second or any millisecond, okay? And it's right before I start to like break away and move that crate, all right? That's an important number because anything less than that number, I am at rest. And that means that the friction force is equal to the pushing force. Anything over that number, now I'm in motion. If I'm to the right of that number, I am in motion, okay? So now what happens is there's going to be a friction force dependent on what we call the kinetic coefficient. So there are two numbers for the coefficient of friction, all right? One is static and one is kinetic. The static one is when I'm at rest. The kinetic one is when I am moving, all right? We'll talk a little bit more about that when we turn the page, but that's what this chart represents. It's kind of the behavior of the progression of the the pushing force in relationship to the friction force. Okay. Now, if I go back over here, kind of getting that explanation of things, we can fill in a couple more blanks here. So when we have static frictions means that we are not moving. Okay. Static friction means we are not moving. Again, the book calls that equilibrium, but I be a little careful with that. When in the static friction zone right here, that means on this side of that maximum friction force, the friction force F is blank, the applied load P. It's going to be equal to that applied load P, or the same as, right? So on that left-hand side of the maximum friction force, this side right here, 45-degree angle, whatever I push with, my friction force is going to be the exact same number. Now, the direction of the static friction force will be opposite the direction of impending motion. Okay. So for that block, since it's being pushed to the right, the friction force is going to the left. It's opposing motion. Now, when we look at kinetic friction occurs on the right-hand side of that maximum friction force graph. So as we said, if we get over that maximum friction force and we're over on the right-hand side here with our push force, now we have entered into, we are moving, okay? And our friction force is going to be dependent on the coefficient of kinetic friction. So kinetic friction means we are moving, okay? We are moving. There is friction there, but we are in a moving state, a dynamic state, if you would. The kinetic friction force Fk is blank, 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 the maximum static friction force. So if we look here, you'll notice that this little bit shorter line, there's a little dip, and then it's going to continue a horizontal line. That is called Fk. That is the kinetic friction force, okay? That means that that's the force when we are moving that is being pushed back because of the two forces that are engaged with one another. So the kinetic friction force is less than the maximum static friction force, which is the Fm. Okay. Now the direction of the kinetic friction force will be opposite again, the direction of motion. Because it's still, even though it's a different value, it's still going to oppose the motion, okay? We have to still overcome it. All right, any questions there on the items we see? Okay, so then what we're gonna do is we're gonna turn the corner. Coefficients of friction, all right? Now, there's an equation for the static friction. So maximum friction force, Fm, there's an equation 4.8 in our book. It's at the bottom of page 203, and it's right down here. So the maximum friction force, which is Fm, is going to be equal to the coefficient of static friction. This is mu, that's a Greek symbol, times the normal force, okay? So if we look at our diagram here, to calculate that friction force, we need to know what the normal force is. In this case, it's going to be equal to the weight, right? We can kind of see there's other forces that are present. Then we have to figure out what our normal force is, and we're going to multiply that by the coefficient of static friction. Okay. Now, the coefficient of static friction is a number that is going to be dependent on the materials that are in contact with one another. So on page 204, table 4.1, there is a list here of common materials that are in contact with one another on a semi-regular basis in like industrial applications. But these are the ranges of the coefficients of friction. So for instance, if we have metal on metal, there's a range here of 0.15 to 0.6. Now you can imagine that's going to depend on the surface finish, obviously, how rough or smooth that finish is. So that's why there is a range there. Now, as we look down to the bottom, you're going to notice that these numbers gradually get larger and larger. And as you look at the different materials that are in contact with one another, kind of makes sense. It's going to be, if you would, the roughness that we see. The one on the bottom here, rubber on concrete, notice that there's again a range of 0.6 to 0.9. The highest value for coefficient of friction is 1. Okay, it's always going to be a decimal value. So the higher that we get, the rougher or the stickier those surfaces are going to be. Now, in the case of rubber on concrete, you can imagine that refers to your tires on concrete when we're driving, right? So as we know, the better tread that we have, the newer the tires are, we're probably closer to, and we want a nice high number so that we stay on the road, right? When we start to get wear on our tires, that number will come down, all right? So you want it to be, you know, nice and high, but over time, naturally, that's going to occur, and we just want to be sure that we're in a safe range. That makes sense. But so coefficient of friction multiplied by the normal force, okay? Now, there is also going to be, a kinetic friction. So we want to calculate the kinetic friction force, which is Fk, okay? That's going to be equal to the kinetic coefficient times the normal force. Now, in the problems that we do that want you to calculate a kinetic friction force, they will give you the kinetic coefficient, all right? But in the case of statics, we're either going to be calculating or we'll get it from a table, or it'll be given to you as well. We mostly deal with static, again, just because of the nature of the class that we're in, okay? Now, coefficient of friction, I've been talking about it. We've been pointing at it here. What I want you to do is, if you want to look in your book, if you want to pull up on your phone, I'd like a definition for coefficient of friction. I want you to find a definition for coefficient of friction. So everybody, what I'd like you to do is just do a little bit of maybe a Google search, or open up your book and take a peek, and let's find out what coefficient of friction is. We kind of looked at numbers. We kind of looked at how it's calculated, but how would we define it, or how would we describe it? And I'll look to those. Oh, great. I was just going to say, Gabrielle says, a number describes that how much friction exists between two surfaces. Well, now that is a great start. And the only reason that I say it's a number that describes how much friction. Now, remember, friction is a force. So coefficient of friction is not a force, but it helps us to calculate the force, all right? And you're right, it's always going to be for two specific surfaces. But let's build on what Gabrielle started out as. Anybody else have something you want to say? Tyler?
It's a ratio of the friction.
It is a ratio, yes. So it's a ratio. And I think that's an important thing to say, because of the fact that it's unitless, all right? It's not going to change the units that we have. So a coefficient of friction is just going to be that decimal number that's going to be a multiplier by the normal force to help us to understand the resistance or the friction that is going to oppose the motion, right? Okay. And then, as we saw earlier, and you can add or subtract this, but as we get surfaces that are going to be rougher or smoother, those numbers are going to increase or decrease with a maximum of 1. All right, so we've got ratio, we've got how much, to help us get to that point where we can figure out how much force exists due to friction on two surfaces. Anything else anybody wants to add? Sounds good to you? Yeah. It is a little elusive, because sometimes when we talk about a coefficient, yes, perfect. It's a ratio. It's unitless. I'm going to put that in here too. I'm just writing kind of words. Unitless. Okay. And helps determine, doesn't really help. It's needed to determine the friction force present. So whenever you are tasked with identifying or calculating a friction force, you either have to know what the static friction force is, or it's given to you, or you have the ability to calculate it, okay? All right. Now, as we look down to our next section, this will help us to calculate it, the angle of friction, okay? The angle of friction. So if we look at back at the illustration that we have here, and I'm going to use the B part of figure 411. You'll notice that we have that friction force coming in, impending in opposing motion. We've got the normal force going up, which is perpendicular to that surface. So we've got two forces that are 90 degrees to one another, right? And as you can imagine, if we've got two forces that are 90 degrees to one another, there's a resultant force in here, isn't there? Okay, there's a resultant force in there. Okay. Because there's that resultant force, if we find this angle right here between the normal force and that resultant, that angle, it's not theta. We don't call it theta, we call it phi. So it's going to be a circle with a vertical line going through it. The numerical value of phi, or the decimal equivalent of the tangent of phi, is going to be the static coefficient friction. Okay, so we go back over here. I'm going to draw that diagram one more time. So I'm going to draw my little box because I want you to have something where you can kind of see how it's developed. Here's our surface. We have the weight coming down. We've got a normal force. Okay, normal force. And then we have that friction force. I always do a F sub F because friction force to me. And if we kind of do our lines and we put our resultant in here, okay, the angle to the vertical is going to be phi, the vertical, and between the vertical and the resultant force. Now, as I look at phi, I can say that tangent of phi is going to be equal to side opposite would be the friction force divided by the normal force. So the side opposite that angle, so if the angle is right here, okay, side opposite would be the equivalent of the friction force divided by the normal force, okay? So tan phi is going to give us then a decimal number, okay, which is equal to the coefficient of static friction. Okay. So if we know the friction force and we know the normal force, we can calculate what the coefficient of static friction is. Okay. All right, just as a reference, all right? Like I said, many times it's going to be given to you in problems, but that's where it comes from. Okay, that's where it comes from. How steep or shallow, if you would, that resultant force is what determines the magnitude of that friction force. Okay, so that's kind of concepts. Let's look at a little story problem here, a little case study, if you would. So this is not in your book, but this is, if you would, our first practice problem, but this is part of our guided notes here. So it says we have a 600-pound block rests on a horizontal surface, and they want us to determine the friction force if the applied load is equal to part A, 100, part B, 200, and C, 300. They're giving us the coefficient of static friction equal to, 0.4, and then the kinetic friction coefficient equal to 0.3. So what we want to do is, I'm going to draw a diagram first. I'm going to grab out my straight edges here. Let's see if I have my... Well, not seeing my protractor, but that's okay. So I will use this instead. So I'm just going to draw a simple block, okay, on a surface. All right. And that block is going to have a weight that is the, the middle, and it's 600 pounds. Okay, 600 pounds. All right. And then we also know that an applied load is equal to, so our applied load is going to be a pushing force. Okay, we'll call this P. Okay. And that's going to change. You know, part A says 100 pounds, part B says 200 pounds, and part C says 300 pounds. So we want to determine what the friction force is for each one of those pushing forces. Okay. Now, some other forces that are acting here. So these are, if you would, the known applied loads. We know the weight and we know the pushing force, but because this is resting on a surface, we also know that there is a normal force acting, right? There's a normal force. And because this is going to move to the right, that means that going to the left, there is going to be a friction force, right? Friction force.
On our free body diagrams, do we have to kind of put the friction force that low or?
I like it because that's where it's acting. So I think it's a good idea to put it there. Where do you mean by put it that low?
Kind of when I do a free body diagram, I just do kind of a cross and have the friction force opposing the P.
So that's okay, but in some problems when when we need to determine a height of something. So for instance, I think in one of your application problems, you're gonna have to calculate a height. Then you're gonna have to have it where it's actually acting because it's gonna be an offset
Okay,
distance. Yeah, so I think it's good to represent it similar to what we see here. Okay. Now, we want to know if what the friction force is at each one of those loads. Now, what I want to do, because this is how every time we have a friction problem and we start pushing on something, we are always going to have the behavior that we saw earlier with the pushing force and the friction force on that little table or that graph. And we are going to have a section where, again, this is 45 degrees, okay? And it's going to go up to a maximum friction force at the highest point on that graph, okay? And I like to say that's my dividing point, okay? That's my dividing point on my graph where anything to the left, we are at rest, okay? We're not moving. And anything to the right of that, we're moving, okay? All right. And we also know that if we are on the left-hand side at rest, then my friction force is going to equal my pushing force. Okay, right? Because I'm not moving yet. So it's balancing it out, if you would. After that, though, I know that my friction is going to take a little dip. And it is then going to continue while it's moving, where that is going to be the kinetic value of the friction force, okay? So what we need to do is we need to find out when I'm pushing with 100, am I on the left or the right side here of my graph, right? Okay, because that's going to depend on if I'm going to use the static coefficient or the kinetic coefficient to get my value for my friction force, okay? So I need to calculate my maximum friction force first to then determine what side I'm on. Okay, so that's going to be my step number one. Now, let's put our convention up here because we will be summing some forces. I don't think we'll be doing any moments, but we will be summing some forces. So maximum friction force, okay? On the previous page, the maximum friction force is going to be equal to the static coefficient times the normal force, okay? So we know that to be static coefficient times the normal force. Always write out your equation in variable form first. This tells me what you're going to do. Now, if we look here, we know what the coefficient of static friction is. That's the 0.4, right? So that's going to be my coefficient of static friction right here. So I know that value here, but I don't have a value for my normal force. So I need to calculate my normal force. How am I going to find my normal force? It's a vertical force. It should be 600 pounds, but how did you do that in your head, Jesse? You're correct.
Wait, that's on.
Now talk it in statics terms. How did you do that?
In the Y direction.
In the Y direction, yes. So to get our normal force, we would sum our forces in the Y direction equal to 0, right? We're in equilibrium here. So in the Y direction, I have a negative 600 pounds, and this is why we have to have our convention, because our convention lets us know what's positive and negative. And then I have a positive normal force because I have it pointing up. equal to 0. And then now when I move that 600 to the other side, you were correct indeed, Jesse. And you are going to start looking at these like, I see it, but you got to write it out for me yet, okay? This is going to be 600 pounds, all right? So now that's going to be the value then that we can use up in our equation. So we're going to take 0.4. It is unitless, remember. Coefficient of static friction is unitless, right? Times 600 pounds. Okay. So my maximum friction force, what do we get? 240, right? 240 pounds. Okay, now that is not an answer that they're asking for. They're asking for determine the friction force when I'm at 100, 200, and 300 pounds. Now, if I know that my maximum friction force here is 240 pounds, that means anything on the left-hand side is not moving. And that means my friction force is equal to my pushing force. So that means for 100 and for 200, I can determine my friction force. So I would say part A here, F friction is equal to. Now, if I'm on the left-hand side of that curve, remember, my pushing force is going to be equal to my friction force. So if I'm pushing with 100, if this is 100, what is this value? It's not 240. 45 degrees, it's 100, exactly. So remember, my pushing force here is going to be my friction force here, because when I push on it, if I'm not moving, my friction force is pushing back with 100. It can go up to 240, but if I'm applying 100, it's not pushing back at me with 240, it's pushing back at me with 100, right? Newton's what law? Which law is that? Equal but opposite force?
The third.
It's the third law, yeah. Yeah. See, you get physics and statics at the same time. Aren't you like totally getting my money's worth here? Yeah. So this is going to be 100 pounds. Okay, so that's a answer. All right. Part B. My friction force is going to be equal to, if we go up here, part B says, all right, when I am applying 200 pounds, 200 pounds is still to the left of 240, right? So that means I'm still on my 45-degree angle. So if 200 is my pushing force, do you see how 200 is the friction force? Does that make sense? Yeah. So not 240, it's not pushing back with 40 more pounds, it's equal to. Then the last part C, 300 pounds. Now what's happened is I am on the right-hand side of my maximum friction force, right? I am now moving. So I am pushing with 300 pounds, Notice that it crosses the line here at the kinetic friction force. Now, the kinetic friction force will always be less than the maximum static friction force. And there's a couple of reasons for that. I know you have all felt when you start pushing something, it's almost kind of harder to get it going. And then once you kind of get it going, it's easier, right? Couple of reasons. Number one, you've got momentum with you, right? You've got some mass behind you. You've got some, you got that moving. That's going to help you stay in motion, right? The second part of it is as at the, I don't know, and then sometimes you can see surface finish, but other times it might be too smooth surfaces, but there are peaks and valleys on the surface of those materials that are in contact with one another. As they move, as those two surfaces move relative to one another, you can imagine that they're wearing the surfaces away and they're naturally getting a little bit more smooth because they're moving, all right? So that's why there is always two values for the static version and the kinetic version of the same two materials that are in contact with one another, all right? So it'll always be a little bit less. So notice that our coefficient of kinetic friction for these same two materials is going to be 0.3. Now, the equation for the kinetic force is going to be using that coefficient of kinetic friction times the normal force, all right? So the normal force is still the same because we haven't changed blocks, right? So the normal force is still going to be 600, but for part C, our kinetic friction force is going to be the coefficient of kinetic friction times the normal. So it's going to be 0.3. Now again, unitless, so there's no units to put in back of there, times 600 pounds. So in this case, our kinetic friction force is going to be, I think, 180 pounds, right? And that'll continue to be 180 for every force after 240. Okay. It's only going to push back. So that means that when I'm pushing with more than 240 pounds and I'm getting the kinetic friction at 180, I'm accelerating because I've got a net force then, right? So those are, if you would, part A, B, and C. Any questions on that problem? So kind of a review of friction. I'm sure you've probably seen, these elements in your friction class or in your physics class, and probably did some experiments related to it as well, maybe calculating coefficients of friction and such. Okay. All right. Good. Next thing we're going to do is we're going to go to problem 486 on page 216 in our books. So I'm going to head here. 216. There we go. All right. Now we are going to be doing problem 486 twice. We're going to be doing it here as a practice problem as written in problem 486. And then for your homework problem, you are going to be doing an application problem, but I change up the numbers and you're going to be solving for something a little bit different. Okay. So let's read the problem statement here for 486. It says we have a 200-pound cabinet is mounted on casters that can be locked to prevent their rotation. The coefficient of static friction between the floor and the casters is a 0.3 value, no units there. Assuming that the casters at both A and B are locked, determine the force P required to move the cabinet to the right and the largest allowable value of H if the cabinet is not to tip over. Okay. So there's two parts there for us, okay, that we are going to be calculating. A little different than I thought. That's okay. All right, so let's draw our diagram. First things, we want to make sure that we put our convention. Okay. Then what we're going to do is we're going to draw our cabinet. Oh, it says just part A. That's what we want to do, just part A. That's why I was like, wait a second. I didn't think we were going to do a height for this one. That's going to be something that you do in your in your application problem. So we're just going to do part A today, or for the practice problems here. So we just want to determine force P required to move the cabinet to the right. Okay. So we know that in the middle here, we have a weight. Straight. A weight of 120 pounds. Okay. And then we know that there is going to be a pushing force. We're not concerned about how high that pushing force is. That would be the part B, but we're not going to be working on that right now. But we're going to call that force P. Okay. Now there is point A, the back casters, and then there's point B, the front casters. Now we are going to put all of the, if you would, the weight at the front, meaning that the normal force is going to act here. Okay. And the friction force will also be acting at that front corner B. Okay. Now, the reason we're doing that is it wants us to know what is the force required to get it moving. So to the right. So that just means that we're going to be kind of almost lifting it up, that I'm not going to say that it's off the floor at A, but almost no force is going to be at the floor at A. And almost all of it is going to be here at B. Okay. As it moves along to kind of get it going. Okay. All right. So if we want to calculate what P is, to get it moving, we need to figure out what is that friction force. And I'm actually going to change this from the F to the M, because we need to know what the maximum friction force is, because that's the point right before it's actually going to start moving. Okay, so whatever number we get has to be greater than that number, all right, for the maximum friction force. Okay, so as we look here, what we're going to do is to find that maximum friction force, we know that that is going to be the static coefficient times the normal force. So the first thing we need to do is find that normal force, because we do know the static coefficient is 0.3. So we'll use that in just a little bit. So we got to find the normal force. So to find the normal force, it's a vertical force. How are we going to find that vertical force using our illustration that we have here? Yes, Jesse, just like last time, you're right. We're going to sum our forces in the y direction equal to 0. Okay. So we've got a negative 120 pounds this time, plus N for our normal force equal to 0. Moving my 120 to the other side, my normal force is going to be equal to 125 pounds. All right. That's the number that we're going to put in here for that maximum friction force. So our maximum friction force then, kind of put it down here, is going to be equal to 0.3 times the normal force, 120 pounds. My maximum friction force, and again, this is that highest force on that curve, right before it stops moving, and you should get 36 pounds, right? So that's not a final answer. Now, because we know that that is going to be the point friction force, P, this is going to be the maximum friction force, okay? This is going to be our kinetic friction. This point right here, we know that that is 36. That means to get it moving, is it going to be equal to 36? Or is it going to be greater than 36? Greater than, because we want to be on this side, right? Remember that maximum friction force is right before it's gonna start moving. So that means that our P needs to be equal to, I guess, something greater than 36 pounds. Is that how I do that, right? How come I'm always like nervous about that? P has to be, I'm not going to put equal to, has to be greater than 36 pounds, right? Makes sense? All right. So that's part A of that problem. The last problem is my favorite. That means it's really fun. The last problem that we have I should say, before we go to the next one, any questions on this one, kind of as we look at the items here? Okay. Look at a ladder problem, okay? This is, again, kind of a little case study. It's not a problem out of our book, but we have a 25-pound uniform ladder. All that means is if we look at the ladder, we can put the 25 pounds at the geometric center to, rather than distributing over its 8-foot length. Rests along a smooth wall. A 175-pound person climbs up the ladder to a point A, okay, at a distance L from the bottom of the ladder before the ladder slips. If the coefficient of friction between the ladder and the ground is 0.4, what is the distance L if the angle between the ladder and the ground is 60 degrees? So let's kind of put this in context, okay? So I'm going to make a vertical wall, okay, something like about like that. And then I'm going to make a horizontal floor, okay? Now it's telling us that the ladder is going to be at a 60-degree angle to the ground. So maybe something like about like this. This is going to represent my ladder. So this is going to be my 60 degrees. Okay. Now this ladder, the entire length here, okay, this entire length of my ladder is going to be 8 feet. Okay. And I know that at the geometric center, 4 feet up, so I'm going to go about half right here, right? That looks about half. 4 feet up from the bottom. Okay. Let me make this a little bit shorter. I can concentrate the weight of that ladder. And I know the weight of that ladder to be 25 pounds. That's the weight of the ladder. So a 25-pound uniform ladder, I can, at the geometric center, concentrate the full load or the full weight of that. Now I have a 175-pound person is going to climb that ladder. Now I'm going to assume that they're going to be higher than the 4 foot. Okay, so this is going to be 175 pounds. Okay. And they're going to climb that ladder a distance L. Okay, so we don't know. We want to know how high can they climb up. That's what we want to find. That's this problem. So we want to find this distance L. Okay. That they can climb up without that ladder kind of kicking out and falling over. Okay. So these are our 2 applied loads. We've got the weight of the person that's climbing up the ladder, and we have the weight of the ladder. Now what we need to do is add our supports. It's supported in 2 places, down at the floor and on the sidewall, if you would. Okay. Let's start with the wall. Okay. It tells us that there's a coefficient of friction between the ground and the ladder of 0.4. Okay, so what that means is if you got to kind of think about how this is going to move. If I'm pushing down on the ladder here with its weight and the person, this ladder is going to want to move this way, right? It's going to want to actually, the motion is going to go to the right. Do you guys agree with that, right? So that means the friction is going to oppose the motion. So the friction force, we're going to call this point B, okay? Or we can call it actually A. We're going to call that point A. That's our first point. The friction force here is going to be going to the left. So this is going to be FM. So this will be the maximum friction force because we want to know when is this going to slip, if you would. So we're going to be at that highest level. And we know this to be coefficient of static friction times the normal force, right? We also know that if this is where the ladder is, that is also the point where our normal force is going to be, right? Our normal force. Right? So the other place that there is support is up here. We're going to call this point B, okay? This is considered a smooth wall. It didn't give us any information, so it doesn't say that there is a coefficient of friction up here. So we're assuming it's just a smooth wall that it's up against. So there's not going to be any friction force here. There will just be a normal force, if you would. We're not going to call it a normal force. We're going to use that for down here, but we're going to call this Bx, and that's going to be a force that is going to be perpendicular to the surface that our ladder is riding on. And the surface is vertical, so that means that its support force is going to be perpendicular to it, and we'll call that Bx, okay? Now, as we look here, we've got 3 unknowns. We've got a maximum friction force unknown. We have a normal force unknown, forces-wise, and a Bx. And we know that we need to calculate our L as well. But as far as forces, what I want to do is I want to try to calculate as many as we can right now. Is there any way that we can calculate Bx at this time? No, because we need the maximum friction force, right? Because those are in the X direction, and we don't know either. Can we calculate the maximum friction force? We know the coefficient of static friction, and we need the normal. Can we calculate the normal? Jesse says yes. Yes, we can. Yep. Jesse is the expert of sum the forces in the X or the sum the forces in the Y. So the first thing we're going to do is we're going to sum our forces in the Y direction equal to 0. Don't forget convention. Don't forget convention. Because otherwise we're going to look at some of the forces in the Y and be like, why did they put a positive and a negative? I don't understand. So as we look here, Y direction, we have a negative 175 pounds. We've got a negative 25 pounds. And we've got a positive normal force. Set that equal to 0. So it looks like this is going to be a negative 200 on this side. We're going to move it to the other side. Our normal force is going to be equal to 200 pounds. All right, so if that's the case, then I can calculate my maximum friction force, right? So I can say maximum friction force is going to be equal to static coefficient times the normal force, and we now know both. So we know 0.4, coefficient of static friction, times 200 pounds. So the maximum friction force is going to be, I think, 80, right? 80 pounds. There we go. Now, again, these aren't final numbers yet, right? We're going to use these along the way. Now that we know the maximum friction force is equal to 80 pounds, can we now calculate Bx? Sure. We can sum our forces in the X equals 0. This is like fun. So if we sum our forces in the X equals 0, so I should say this was my number 1, this was my number 2, this is my number 3. So if we're kind of looking for order here, we would have a Bx positive minus 80, because it's pointing to the left, pounds is equal to 0. So my Bx is going to be equal to 80 pounds. You get the idea that statics is kind of easy or kind of intuitive. You can kind of see it sometimes, right? Especially when there's not too many forces. So this is going to be 80 pounds. All right. Now, I'm not to where I need to be because I want to ultimately find L, but I do know now all of the forces that are acting, support and applied loads, right? And that's where I want to be if I can find my L. All right. So as we look here, I want to find what L is, right? Now, the last equation of equilibrium, some of the moments around a point can get me that distance, right? But unfortunately, if I look at the direction of the forces, which are vertical, and horizontal, and vertical, they are not along a 60-degree angle, right? Do you see that? So the L is not going to be a perpendicular distance that I can calculate, right? But, if I kind of go down here, right? And if I go down here, and if I find a perpendicular distance from here to here, I can now find this. So if I sum my moments around A, I need the perpendicular distance to any offset forces causing rotation. The first one will be Bx. We're going to call this H for height, okay? So that's going to be that value. Then the next one that I have here is going to be the perpendicular distance to the 175 pounds. So if I go from A to the 175, I'm going to call this D1 or D2. And then to the 25, I'm going to call its perpendicular distance D2. That makes sense to everybody? Do you kind of see where we're going here? So this is a 90-degree angle, 90-degree angle, 90-degree angle to point A. We're going to sum around A. Now, if we kind of think ahead, right? We need to know these values for H, D1, and D2, right? We want actual numbers because we need to find L. We want to get down so that L is our only unknown, all right? So that means that we're going to determine the magnitudes of H, D1, and D2. So go ahead and write down, based on the information we have, can you find the magnitudes or the magnitudes of these distances in terms of their hypotenuse for any one of these. I'll give you a little bit of a chance to kind of write down your thoughts if you would. Remember that you have 60-degree angle here to the horizontal that ladder is making. You get H equal to 6.928?
Yep.
Okay, excellent. That one we can get an actual number for because we know the hypotenuse is 8. We have 60 degrees, so we can take the sine, right? Side opposite over the hypotenuse to get, or the side opposite, which is H over the hypotenuse, and then solving for H, it would be sine of 60 times 8 feet. I'm going to do D2 next, just because I can get an actual value for that one. So that is also, it's going to be this time side adjacent. So that's going to be the cosine of 60 times the 4 feet up. That's its hypotenuse. So D2 should be 2 feet because cosine of 60, I think is 1/2, right? Okay. And then the last one that we have, I'm going to kind of go over here. D1. D1 is the distance perpendicular to 1.75. Its hypotenuse is going to be L. And then we're going to also take the cosine of 60 times L. So that means since the cosine of 60 is 0.5, it's going to be 0.5 L in terms of that hypotenuse. Because remember, L is going to be what we're going to actually solve for, how far up the ladder the 175-pound person can be. So I'm going to put D1 is equal to 0.5 L, D2 is equal to 2 feet, and then H is equal to 6.928 feet. Okay. So now we have all of our distances, and we're gonna find that the only unknown that we have is going to be L. So the next step would be to sum our moments around A to solve for that distance L. Okay. So to do that, I'm going to just kind of try to get my diagram here. So I'm going to start a new piece of paper just so I can have it here instead of flipping the page. But I'm going to sum my moment around point A equal to 0. So that means I'm going to put my finger over the top here, and then I'm going to pull in the direction of these 3 offset forces to then solve for L ultimately. So I've got BX. BX is going to rotate clockwise. It has a magnitude of 80 pounds, and its perpendicular distance is going to be the 6.928. So I've got 80 pounds times 6.928 feet. And it is going to rotate clockwise. So that's going to be a negative out front. Put my finger back on A, pull in the direction of the 175. That's going to rotate counterclockwise. So that's going to be a plus this time. 175 pounds times perpendicular distance D1, 0.5 L. Then the last one is going to be the 25 pounds. That's also going to go in a clockwise direction. So 25 pounds times perpendicular distance, 2 feet. equal to 0. Make sure you do equal to 0, and then also make sure that your only unknown here is L. And again, L is how far up that ladder that 175-pound person can go and safely, not fall. Okay, so go ahead and solve for L in your problem here. Should get a value for L, meaning from the floor all the way up to where that person can stand is going to be 5.76 feet along that ladder. Okay. So questions on that problem? You will see another application problem that's related to ladder like this, similar, but I think you have to calculate for something else. You will also see it on your final exam for sure. Something like this, just so you know. I like these. You'll also probably see one with a crate because you'll see that in dynamics again too. Students just remembered it last week when we had it. Okay. All right. With that, that means if we get to the bottom of the page here, it says now you're ready to start the Module 7 application problems relating to friction. Okay, so relating to friction. So what I'm going to do is I'm going to stop the recording here, and then we'll look at your application problems so you can kind of get an idea of what you've got ahead.